Continuing metric spaces, we have studied neighborhood and open sets in topology. Now we are studying them in metric spaces. Neighborhood of a point. The concept is same, it's only under the concept of metric spaces. Let X be a metric space and capital A will be any subset of X. Then A will be neighborhood of a particular point. A subset A of X is called neighborhood of a point X if there exists an open sphere of some positive radius and that sphere is contained in the set A itself. The open sphere will be centered at that particular point X and will be of some positive radius. So if there exists a real number R positive such that the sphere centered at X with some radius is contained in A, subset of A. Suppose this is A, X is a point, and we are considering the open sphere centered on X and that sphere contained in A. Then we say A is neighborhood of X. Writing the sphere is both way correct. Sx R at the index or Sxr. For example, let Rd be a usual metric space with usual metric dxy is equals to mod x minus y for every x and y belongings to R. Considering A be any subset of R, let A is equals to minus 4 2 interval which is a subset of R. We are considering any subset of R. And now consider a point. A is neighborhood of point x is equals to 1 with respect to the usual metric. See, A is minus 4 to 2. 1 will be inside A. Since there is an open sphere centered at 1 and radius we are considering as half, we can take radius any number, but the point is we need to choose radius in such a way that sphere is contained in A. Suppose this is set A, minus 4 to 2 on number line, 1 is a point, we can have an open sphere. If there is no possibility of such radius, we cannot make such open sphere which is contained in that set, then A won't be neighborhood of 1. So in this way there is a possibility. Sphere is contained in A, therefore A is neighborhood of 1. Next concept is open set. We have just read the concept of neighborhood. If a set is neighborhood of each of its points, then the set is open set. That's the only thing in this definition. Let X be a metric space. Subset A of X is called an open set if every point of A is an interior point of A, or if A is neighborhood of each of its points. See, point is interior of a set and A is the set is neighborhood of point. Both are the same concept, same meanings, just the other way of writing it. If for every A belongs to A, we have a sphere, open sphere with some radius contained in that set, and this statement is true for every element of the set, then we say A is an open set. A is neighborhood of each of its points. On real number line, AB interval is an open set which is a collection of points lying between A and B. The questions based on this, let Rd be a usual metric space with metric dxy is equals to modulus of x minus y for all xy belongs to R. Find whether or not the following subsets of R are neighborhood of 1. We need to check for if they are neighborhood of 1 or not. Intervals are given 0 to 2, 1 to 2 closed, 0 to 2 closed minus half, fourth is real. Now see, in case of first open interval 0 to 2, since 1 lies inside the interval, we can make a sphere with some positive radius that will be contained in this particular set. So A is 1 here, capital A is 0 to 2, R suppose I'm taking half. So there is a choice of radius available on which the sphere will be contained in A, right? So A is neighborhood of 1 in this case. Similar in the second one. In second one, A is not neighborhood of 1 because 1 is at the boundary. So we discuss it further. In second part, the interval is capital A is 1 to 2 closed and small a point is 1. We need to discuss about the neighborhood of 1. So we can't have an open sphere with any positive radius that will be contained in set A because 1 is at the boundary. However small radius I may choose, the sphere will go out of the set A. See, this is the condition. At 1, the sphere will always go out of the set because it is at the boundary. So A is not neighborhood of 1 in this case. In third case, there is a interval 0 to 2, only point half is excluded. So still we can choose the radius centered at 1. We can take radius as 1 by 3. Availability of radius is there. We can choose radius 1 by 4, 1 by 5. So many availabilities of radius on which when we make sphere that will be contained in A. Real numbers collection is always neighborhood of each of its points, so there is no doubt about it because it's the whole number line minus infinity to infinity.